on this computer, and we're on air. We're talking about paper by Frederick Eberhardt, Introduction to the Foundations of Causal Discovery. I have that in front of me, and I'm sort of going by the paper in front of a whiteboard practically. What the paper is about and why it is interesting, I think Frederick said it well in the abstract. The goal is to indicate that for a large variety of different settings, the assumptions necessary and sufficient for causal discovery are now well understood. I need to mute something on my side, but sorry about that. So he convinced me. Let's see if we all will be convinced after this. And of course, we do causal discovery every day, the same as we do linear algebra. I'm just kidding. So because we don't, let's go through his introduction, because he does like a really good job explaining what is what and what is it about. So his example is the wine and cardiovascular disease. So you all know, probably have heard of this folk wisdom, but that one glass of wine a day can only make your life better. And there is a whole debate, apparently in 2013 or some edition of Scientific American had a whole publication about this. Somebody view it as a misconception, when, well, wine lovers obviously don't view it as a misconception, and so there is a whole debate that is that true or not. So what people are usually leaving out is the common cause of socioeconomic status. So if you think about like when we talk about, okay, let me just try it here. When we talk about wine drinking and cardiovascular disease, let's say it's CD, like that. So we're thinking, okay, there is a causal relationship between wine drinking and the disease, because we observe some correlation in the data. Oh, look, we can predict it. Our CNN can predict disease from wine drinking, really. So that must be it. Stop wine drinking, and then CNN cannot predict it, or then you'll be healthier. But the problem is that socioeconomic status is a common cause of both of those. So when we have this situation,
I will interrupt that the paper didn't actually take a stance on it. It explicitly said that it doesn't take a stance on.
the paper does not. I do.
Oh, yeah, okay.
Yeah.
Just trying to
Yeah.
keep you honest.
But I did not put a stance. Yeah, but I didn't put a stance yet, right? I do implicitly. I did not say my opinion either. I don't know why you're like defending the paper.
I'm just messing with you.
Yeah. But the problem is, so people with higher socioeconomic status can afford wine or better wine or whatever, and that could cause them the wine consumption. So when we see, oh, okay, people who drink hard alcohol, they could be lower socioeconomic status, and they wouldn't have hard benefits from drinking hard liquor, cheaper liquor. But people who drink wine, they sort of have benefits for their heart, but in fact, it's just they have better access to healthcare and other benefits that come with higher socioeconomic status. And what we observe here is just an effect that we're not taking into account this variable. There is a relationship or correlation between those two when we only consider those two alone. So, but yeah. I think I have my slides are my notes for me. Yes. So what we want to do is to establish if there is that link or there is a common cause, or what we want to do is to eliminate the common causes, is to do a randomized experiment, or actually it's a very simple rule, randomized assignment. Make people at random drink a lot of wine. Some people order them to drink a lot of wine, and some people order not to drink a lot of wine. And then we have, by doing that, randomized assignment, cardiovascular disease. And um, just a side note, we usually assume that those arrows, those causes are probabilistic. It's not like 100% like a gear turning another gear, a cogs connecting and turning. We're like, we're leaving out some possibility of noise, and another thing that we will come to on a different slide. So, but when we randomly prescribe people to drink and not to drink, we break that link. And then since now one random variable is sort of left loose there, we can figure out if there is still that relation or not between wine and cardiovascular disorder. So that's what randomized experiment is doing, and it works almost always. It's a good thing to do when you can. And although Sir Fisher said correlation doesn't imply causation, so all you can do to know causation is randomized experiment. That's it, because I said so. But from the grave, Sir Isaac Newton said, oh, wait a second, did we do an experiment with the moon and my law of celestial body movements for the causes? Well, we did not. And yet we know with high certainty that moon movement is causing tides, right? And what we mean by moon movement is causing tides is that if we grab the moon and wiggle it a little, the Earth's crust will wiggle and the tides will change. But we never actually done the experiment, but yet we are sure this will happen. So why and how? So the causal discovery that we're going through here, okay, I've done that motion. So yet causal relations are of interest because like when we actually want to intervene, okay, with moon, maybe we don't want to intervene, but our trip to the moon was kind of intervention. We relied on the causal knowledge that we gained from information collection and sort of side experiments. But when we want to predict the system behavior in case of intervention, how it will behave, then we want to know causal information. And arguably, I argue, and many other scientists too, that the whole purpose of science is to figure out causal relationships, not to just able to predict. But we can argue about that later. So probability distributions and all of that statistical inference. Probability distribution does not tell us, let me see, I don't have like, okay, probability distribution, joint probability distribution on all of the variables, probability of xy, x2, x3 is sort of a generative tool. If we can estimate it, we can sample from it, but it does not tell us anything or much about causality at all for various reasons. Even the graphical models don't tell us, the graphical models, just a 3 seconds refresher, is when we factor this probability distribution into xi, xj into a set of conditionals and denote each conditional distribution with an arrow, put a graph. So I, j, and put a graph for all of those variables, graphical model. But there are tons of different ways of how to represent one single joint probability distribution as a factorization of conditionals. And any way you represent them, it's still correct joint distribution. So graphical models, representations of joint probabilities and joint probability does not tell us everything we want to know or much about causality. Okay, what does he say later there? So what there is another inherent ambiguity is when we say probability of cardiovascular disease given wine, does it mean we had, like, it's unclear from this notation if we run a randomized experiment, if we intervene on wine or not. If we did not, sorry, just a second. if we did not intervene on wine. So Judea Pearl, I believe in the early 90s or late 80s, came up with something called do calculus. And again, this is because we want to talk about interventions and effects of interventions. The causality is about it's about counterfactual reasoning, actually. We want to be able to reason counterfactually. What will happen if I do this? What will happen if I do that, without actually doing that? So with probability, joint probability, and this is not in the paper, but I'm kind of mixing whatever is in my head with whatever Frederick thought. When we have joint probability distribution, yes, it's fantastic. We have a generative model. So you can see the progression. We're talking about machine learning is a classifier only supervised. So we have this supervised machine learning and everyone is happy and we're making millions for Google and other companies. But then some people come forward and say, oh, no, we should do generative. Look, VIEs, they're so great. And so the even generative are still like half measure. Like it's slightly better than just simply classification and unsupervised. But yes, we have the generative model, but generative models don't allow us to do counterfactual reasoning. They don't allow us to kind of reason about what will happen if we do this. Like, yeah, so that's an additional notation. But this is actually kind of a off topic, sort of a insert that Frederick added there, because we won't talk much about this further, do calculus. Okay, yes. So causal graphical models, we want to have the same formalism. We want to be able to interpret. What did I not use? Okay. We want to be able to interpret the arrows causally. Yeah, as he says there, the causal models support very strong interpretation, not just about a few points there. I don't think I talk about it. The main thing to have in mind that people in causal learning are interested and are concerned with is direct cause. So when we have this graph, so in a sense, X causes K, but because we have other variables, and we have X causes K through Z, if we want to intervene on this graph and affect K without directly messing with it, say we cannot mess with it, like we want to improve quality of life of patients. Oh, like, okay, go and improve quality of life of patients. Just take it and make it hard, right? We cannot do that. We need to do something else to what we can affect that will cause quality of, improve quality of lives of patients. And so we see that quality of lives of patients, let's take United States out of the picture, but in richer countries, it's higher, right? But maybe not in the United States, but okay, because the healthcare system is a little messed up. But okay, let's make the country richer and eventually the quality of life of patients will improve. So but that's a long way through a lot of multiple chains of, causal chains. If we can find something that directly causes a direct cause that affects the quality of life of patients, and the cause may be both ways. We put one arrow, but what we mean it causes, it could improve or and then we want more of Z, so it's like positively connected or negatively connected, or Z may be causing like lowering the quality of life of patients. So we want to dampen or kind of reduce Z if we can intervene on Z. That's one thing about the graph. Another thing about the graph is, well, we'll get to the Markov assumption next, I think. Yeah, the important part is the direct cause, and another important part is the set of all variables. So when we talk about causal learning and a causal graph, we are concerned with the set of variables that we have access to, and we have to make we have to make an assumption that we measure enough variables to be important. And now I will be throwing a lot of terms there. So we want to assume that our V is causally sufficient. So what causally sufficient means is that if we have some unmeasured variables that we failed to think about, none of them is simultaneously causes any two or more variables in the set V that we measure. Because then we will have relations between X and Y, say, that we cannot explain by the measurements of those wide variable X, Y, Z, and K. Although this is okay, this is allowed, it doesn't break the causal sufficiency. And any arrows to outside are okay. They don't matter for us. So that's one thing. Another thing that could change is that imagine we have these four variables. Imagine we're still talking about the contrived example of mine about patient quality of life. William, I hope it's better than the wine drinking example, although it's more fun to do, but anyways. So imagine that we discovered that Z is direct cause of K, and ignore Y for now. So we're pouring money into this, or like we're leaving our warm couches and going and doing something, so spending energy to change Z. But then we find out that actually Z is not a direct cause of K. There are other variables that we have not measured that are there in between on this path. Originally, as far as we were concerned, this is fine. It doesn't affect causal sufficiency. It does not redirect or destroy the causal arrow. We were correct from the start. Z causes K, but there are other variables that can come up, and we can find ourselves more efficient by if we were acting on this variable, if we could, rather than going to Z up the chain. But given the information that we have, it's we're doing the optimal thing. Let me see what else I need to say here. Okay, well,
one thing I like from the paper was that there was like one blurb about how like we often say correlation's not causation, but he talks about the fact that correlation is usually an indicator of causation, and usually equivalence classes of there's like a set of possible causations.
I'm on page 2. Yeah, I'm on page 2.
Okay.
So I'm not through the introduction yet.
Okay.
Yeah. I discussed set of variables, and let's go through some definitions now. So a path is any sequence of non-repeating edges. So this is a path between A and B, although it's not a directed path. This path, causal information does flow along this path and especially if you condition on this variable, these two become correlated, and then there is a direct path. So things like that. So that's why we need to define a path in general that is not define the path that is not a directed path, just a directed path. Well, directed path is the same, but when you only travel along the directions of those arrows that connect the variables. Descendant is anything down down, like if there is a path from you to someone else, down that directed path, then it's your descendant. Like B is a descendant of A, so that means A eventually causes B. We'll talk about some conditions when causation doesn't imply correlation. And then the child is your direct, when the path is of length 1, is your direct ancestor or descendant.
It seems like figuring out whether something's either a direct cause or a descendant would be pretty hard. Because like if something's after another thing, like you might not have
There is
any.
no after. There is no after. There is no time
No,
involved, by the way.
okay.
There is no time involved yet. But this, yeah, we'll talk about it. This whole thing, we'll talk about it, William. It's about causal discovery. This whole paper is about the field of causal discovery. You're right.
Yeah.
So,
Would you prefer me to just be quiet or chime in?
no, I prefer you to be yourself. Yes, that's
Okay.
fine. That's perfect. I like it. More people should join. And collider is an important notion. Collider is a variable on which, let's call it C for collider. Two paths collide, or two arrows collide on this variable. So very simple. Why they're important, we'll find out soon. Non-collider is important for D-separation, which I think I will talk about a little later. It is important that a path that doesn't have colliders is non-blocking, that you can transfer information from that path. And if there is a collider, you can block that path by conditioning. Blah, blah, blah. Oh, okay. Well, now we're going to assumptions. We haven't defined the problem yet, so that was an introduction. Now the assumptions of causal discovery and everything, we'll define them now. So kinds of inference, again, we want to work with the data. We want to go from the data that we measure, experimental data, or just data that we've collected, or data that somebody else was collecting. And there are three kinds of things that he mentions. It's a super nice footnote somewhere on page 3, I believe. Yes. Statistical inference, causal discovery, and causal inference. So statistical inference is what we're all familiar with, is trying to estimate a joint distribution. Model or estimate the joint distribution is inference from data to generative distribution. Yes. Well, we want to estimate the generating distribution, but ideally we want to do it so that it's generative, so we can use it to sample more data. And then if you're Bayesian and like my MCMC, then you can like estimate additional things from those additional samples so that you can generate. Causal discovery, I will have a definition on the next page. So, but we want to identify from the data, we basically want to identify the causal graph. That's causal discovery of causal learning, but this concerns with it's a too strong definition. Actually, causal discovery, even if we can discover that these two things cause each other and others are correlated, it's already a good start, because then we can avoid making an experiment of figuring out something about those two things that we can just figure out from observational data, from tweets on Twitter or something. And causal inference is, once you have this graph, once you discovered the causal graph, maybe from a randomized experiment, again, maybe from interventions, but it's not everything. You want to be able to quantify the changes if you affect something with this precision or with this strength. how much of a change will you observe in something downstream somewhere. So that's causal inference. This paper is about causal discovery mostly. And the definition straight from the paper, page 3, I think, well, page 83, according to the numbering that I have, is causal discovery is the problem of identifying as much as possible about the causal relations of interest. Well, ideally the whole graph, and given the data set of measurements over variables V, given everything I said before about V, we have to kind of assume that V is all we need for our questions. It's causally sufficient, complete. Okay. Well, okay. So, but then again, can we go from statistical inference to causal discovery somehow? In fully general case, having joint probability distribution tells us nothing about causality. It's not just correlation doesn't imply causation. It's causation doesn't imply correlation either. It's like, what can we do about it? And so we have to come, well, causation doesn't imply correlation, as he says, is not obvious. And I was staring at it for a while and coming up with my own examples. And then I continued reading it so that he has an example as well. But my own example is any kind of a biological feedback system where stuff is a control system. So if you imagine that there are two causes that cancel each other, for like in the cells and the neurons, the polarity is maintained, and if something changes, the pumps are open, and they change and correct the polarity again. But if we're observing just the measurements, we would say, oh, like we wouldn't see that changing of the external polarity changes the internal polarity of the cell because it's self-regulating, but in fact it does. So we'll get to his example in just a moment. Well, D-separation, basically, yeah, like he covered everything in this one little paper, but basically Judah Pearl introduced this notion that is very helpful to think about. If you have two variables, X and Y, I don't know if I can do it on the fly, but let me try. And you have some set C that something's going on in this set C, lots of other variables there that also are measured. We have access to them. Let's try, okay. So if we cannot find a set, the problem is some variables, namely colliders, if you condition on them, you open up the path. And other variables, if you condition on them, if the path is like that, and you condition on this variable, you broken the connection. Now you like A doesn't cause B, you like in your data if you condition on this variable. But if it is a collider, reverse happens. They're sort of, the variables are independent, but if you conditioned on them on the collider, then they become dependent, explaining away a phenomenon. So D-separation tells us which sets, if you condition on them, on all of the variables in that set, will render X and Y independent. So I won't go in the collider detail, but basically by just looking at the graph structure and looking at the colliders and their descendants, you can say if variable X and Y are D-separated, or let's notion of graphical independence. It's not a statistical independence notion. It's not linear independence in no meaning of that word, but
it's like there's causes in between. Is that right?
Well, C is a bunch of so take a graph. This is a full graph. You took two variables from this graph, X and Y. You singled them out. And you looked at all of the paths that go through the graph and connect them. And then you took all of the variables that each path from X to Y went through. And this is your set C. Now,
Oh, okay.
if by conditioning on this set C, you can render them independent, that is, this additional condition about colliders holds, then there's two variables, well, I mean, will become de-separated, but they are actually deconnected because, well, if there is a path, a causal path or direct path from X to Y. So with two assumptions, which we'll cover now because they're super important, causal Markov assumption and causal faithfulness assumption, we can surprisingly say that. And this, William, this is important. The C, it's a conditional dependence or independence. This is independence, graphical independence or de-separation. It's there. And statistical independence, conditional, again. Because if you don't condition, everything is sort of dependent. The classical example is this chain, blah, blah, blah. So if you look at this chain and imagine even it could be one-dimensional physical systems of springs and masses and so on. And you actually only wiggling the leftmost mass, and everything is depending on your K Hooke's coefficient and stiffness of the springs will wobble with different amplitude and different reaction. So if you put your correlation matrix, everything is correlated. But because this movement is correlated with that movement, obviously. But when we want the causal chain, the actual springs, we will have to condition when we measure our correlation, which is called, there is a way to do that, partial correlation, when you condition on everything but the two pairs of variables. And then if you condition on this and the rest and measure correlation between these two, they will not be correlated, because if you pin this down, this mass, and don't let it move, this spring will not move because you will screen out the relationship between this and that. That is sort of related. Okay, bear with me. We'll get there. So two important assumptions, causal Markov assumption. Yes, causal Markov assumptions just tells us that variables are independent of their non-causes. So if we have a variable and some parents of that variable, and those are only three incoming edges to that variable, and the outgoing maybe many. So causal Markov assumption just tells us if we condition on these variables, I should have, okay, let's pick another symbol. If we fix them, then this variable now is independent of everything else, other ancestors of this variable, whatever is happening there, it's only caused by its direct parents, its direct, parents, direct ancestors. The thing that the rant about quantum mechanics there and everything, basically what it translates to is to our conventional understanding of the world around us and the measurements up to quantum mechanics, maybe. It's locality principle. That like you cannot have like spooky interaction at a distance, right? Which apparently we do in quantum mechanics. But in other cases, what it says that, okay, if there is a direct cause and you're not letting any information pass through, then nothing can pass through. That's your only direct cause. And it is hard to imagine violations of this assumption besides when the things were on purpose or negligence done wrong. And so he gives interesting example that quantization, coarse-grained quantization of variables can lead to violation of Markov assumption. So even though those are the parents are there, but because we're not measuring or quantizing correctly, we would see that the information still leaks, although we have conditioned on everything that is a direct cause according to the causal graph. That is true. And we measured that.
So is this just saying everything has a set of variables which determine its state, or like every single variable that we could measure, every single possible observable is completely determined by some set of upstream parents?
No. You are speculating with the word completely. You've never heard it in this conversation, and yet you want to use it, Jack. Okay, what we actually mean, and I was, like there are levels of knowledge, right? What we actually mean is that each of those variables, and I said the relation is probabilistic. What we mean that each of these variables has also some inherent noise specific to that variable. So it's probabilistically determined, but not completely determined, right? First of all, this noise and this noise, they're independent of each other completely. And then if you condition on this variable, yes, this noise, this particular epsilon k will not flow there into that variable, but this variable will continue functioning. And the noises, of course, you want to think about it as a measure of our uncertainty, or you want to think about as randomness of our world on the quantum level. That doesn't matter. Like it's simpler for statistical, in the discussion of statistical discovery, to think about this noise as internal noise of the system that is sort of measure of our uncertainty. Does it make sense? Did I address your question?
I still don't know exactly what the causal Markov assumption is.
The cause of Markov assumption is all of our observations about the world and everything that we built so far, besides maybe on quantum level. And this is questionable too.
Ooh, I just don't like, even on the quantum level.
No. Don't talk about quantum level.
Okay. Well,
that's what I'm saying. That's what I'm like. Markov assumption is, okay, if you have three causes and you conditioned on them, how come this thing, how can it affect? If I randomly make people drink wine, how can their socioeconomic status affect their wine drinking? I keep them on an island. I took all of them to an island, put them into the rooms separately, and randomly assign them to drink wine. They don't have any credit cards or anything, right? So like if I removed all of the, like, if I remove this arrow completely, how can, how can this variable affect this one if there is no connection?
okay.
I've blocked the path. That's it. It's not going. Either by randomness or by sticking a stick into this, like breaking the machinery.
So the assumption is that these causal graphs, like, I don't know, that they work? Or can you draw an example of a causal graph which violates the Markov assumption?
No,
or
there is no, exactly. There is no causal graph that can violate Markov assumption that we know. Because if there is something still leaking, what we assume is that an observed common cause or an observed path.
So it's basically just the assumption that these sort of graph, like this causal model, works for the world.
The assumption is that works for the world. No. The assumption is that, like, if we have the graph, if we have the causal graph, then by conditioning, so imagine that we have, the assumption is that there is a true causal graph, that
Yeah, that's kind of what I was saying.
Non-locality, the interactions are local, sort of.
Well, local on this graph, not local in like, because quantum is local according to the usual distance metric in three-dimensional space. That's what they're talking about, physicists, right?
Well, I don't want to talk about quantum anymore. I kind of
Well, like that's what locality means in terms of those models. This means local, meaning that information travels only through a causal graph.
Yes, information travels only through a causal graph.
Okay.
And there is no way for us to come up with an example where this is violated, besides that we didn't construct the causal graph correctly.
I've got, right. Okay, I understand it. Thank you.
Yeah. So another assumption is the more interesting, is faithfulness assumption, is that that's kind of more readily violated. It's what faithfulness assumption says is that let me find it, the precise definition if he gives us. William, if you remember where he defines faithfulness, that is the time to have me conditional together, blah blah blah, desperation. No, but faithfulness
It might be page 3. It appears on page 3 a bunch of times.
But it's not explained.
And page 4. I mean, it's all over the place.
Faithfulness assumption connects probability distribution independencies with. Basically, it says, okay, let me wing it, sort of. Let me come it up.
Oh, wait. He says there's a place where he says faithfulness can be thought of as a simplicity assumption, and it is relatively easy to find violations of it. I don't know. Is that it?
Does it help everyone?
I don't know.
I think it's not a definition. Yes, but the faithfulness says that if there is a probabilistic relation, if there is, okay, faithfulness says that, okay, I can define it now. It says that if there is a causal arrow in the causal graph, that means we can detect it by conditional independence measures from the distribution. So that means causation implies correlation. Basically, what faithfulness says is that if there is causal arrow, causation there, then it implies correlation. But again, think about this situation. When one variable contributes positively, another one contributes negatively, and they cancel each other. Perfectly cancel each other, or perfectly because we don't measure infinite number of data, samples of data. Maybe asymptotically we can see it, but it does not. So if they cancel each other, then no tests of statistical conditional independence will tell us that they are related. That's what faithfulness assumption is precluding. It says those situations, we don't consider those situations, or they're impossible in the graphs that we're working. So biological systems are out of the picture if we're talking about like highly feedback dependent systems and stuff like that. And some socio-economic systems also heavily self-regulated. He gives an example of a power generator, backup power generator that so we have a light, we have a computer in your room, a gamer's computer where the kid plays, or an adult kid, and this computer always works. Well, so we can analyze, okay, well, how is this thing powered? and we can never figure out that it is powered by power lines, because when the power lines go down, it still continues to play because backup power generator kicks in and starts feeding it. But backup power generator also doesn't affect it because most of the time it's off. So it's like we cannot figure out the causal link between backup power generator and the gamer's computer or whatever, and the show continues, right? It goes on. So the interesting, now we finally gotten to the super interesting results, is the following. In 1990, Freidenberg and then a year later Vermey and Pearl showed that any two, I'm just reading from the paper, any two acyclic causal structures without unmeasured variables that are Markov and faithful to the same distribution P of V, where V is our set of variables, share the same adjacencies, the same undirected graphical skeleton. Skeleton is when you drop the arrows, the arrowheads, and the same unshielded colliders. So unshielded collider is a collider whose two parents are not adjacent. We already had that. So this would be an unshielded collider, and this will be a shielded collider, or any other connection between the parents. So what they both, well, I don't know, it's an interesting rant, but what they both basically show, the difference between the papers is like yeah, they must be independent. The first paper was in a journal, like a large study, proper journal, and the second paper was a year later at a conference, which is a good conference though, or maybe I'm saying that because I have a paper there, but in any case, they both show that. And the interesting consequence is, look at the skeleton. If you ignore the arrows here, three variable, all possible three directed, three variable tags. That's an important thing that I didn't mention. We don't want any cycles. Cycles are completely excluded here. That's another assumption, a cyclicity assumption. So we want the graphs to be acyclic because, well, those causal relationships are sort of instantaneous, and any kind of cycle is a variable momentarily, instantaneously causing itself through a chain of other variables. Could be resolved through time, but for now, or we can get into a philosophical discussion, but for now, people left it out. There is work that he mentioned that kind of deals with cycles, or tries to. So if we list all of the DAGs for three variables, so again, skeleton, drop the arrow and you see that this is the same graph, and this is the same graph. So basically the graphs that have the same skeleton and all possible arrowhead location are in the same equivalence class. They are indistinguishable by any of the statistical tests based methods that we've discussed. Markov assumption and faithfulness assumption shatters the space of all DAGs into equivalence classes. It does not identify a graph. So interestingly, for the three variable class, all of the colliders end up in the singleton equivalence class, because they are uniquely identified. So think about now implications of that. It means that from observational data, you can uniquely identify colliders. Just from observational data, you don't need to run randomized experiments and things like that, but you can uniquely identify colliders by relying on Markov and faithfulness assumption. That was a big thing that he doesn't talk about it, but in the 90s, lots of good examples of Bayesian networks and inference and in causality, lots of papers and work of Judea Pearl. So that was one, and then it led to, yeah, Markov equivalence class. And yeah, we reduce underdetermination because, well, given all possible DAGs, now we have equivalence classes. That's good, but some equivalence classes are large. For example, think of a skeleton, which is a fully connected graph. It's, what is it? The number of arrowheads, the directions is 2 to the n, right? Because each can be either one way or another. So that equivalence class is huge, but others are usually smaller, especially if your graph resulting graph is sparse, then the chances that you can detect, well, like, yes, here, the largest graph is fully connected. When the graph is sparse, you can, at least this algorithm from the observational data, can come up with candidates that you can analyze and decide which experiments to perform or whether to converge. Oh, we have 5 minutes. I'm talking too much. Whether to, just select one solution. Basically, from this whole research direction, what we've established in theorem 1 in the paper, that linear Gaussian models, this is a vector, this is a matrix, and another vector. Well, kind of the sets, those are your variables, plus epsilon Gaussian noise, some mu and sigma. For these variables and for multinomial random variables, it's when your variables are categorical. We can establish equivalence classes just from observational data. That's that we know that is provable. Then later people started to weaken the assumptions. Like there is there was the PC algorithm which can do that exactly, asymptotically exactly, given enough data that the tests are correct. Conditional independence tests are correct. PC algorithm works. FCI algorithm, that was kind of next one, drops the assumption of causal sufficiency. So what will it do? What will we do if there are unobserved common causes? So FCI algorithm tries to tell you where between each variables. It's not only tells you equivalence class or guesses the directions, it gives you the directions for the colliders where it's absolutely sure that, well, there are through colliders you can figure out, orient other edges as well with certainty. But it also tells you, okay, there is an unexplained relationship. That means there is an unobserved common cause somewhere. Then other algorithms like CCD algorithms drops the acyclicity assumption, and then SAT-based solvers can do more because, okay, well, the interesting segue into SAT-based solvers, you are given probability distribution from which you establish a set of conditional independences tests, and now you have to reconcile all of those independences into a single graph. And that's a constraint satisfaction problem, similar or reducible to a three SAT problem, basically, under the core. That's interesting. So next one, I want to quickly, because it's 3 minutes, but let's still go through that. If you need to disconnect, please just disconnect. That's fine. I don't want to hold it for sure. So next one was super exciting, and it should be super exciting for Trend Center and especially for Vince and like everyone who works with Vince, because it involves independent component analysis, ICA. So linear non-Gaussian model. It is the same as before. You have variables transformed via a matrix plus noise. But now this noise is explicitly non-Gaussian. It cannot be Gaussian. Well, if Rogers is here, at most one can be. In this case, surprisingly, we can uniquely identify the causal graph by using ICA. Not an equivalence class, but uniquely identify the causal graph. The intuition is here. And as I responded to Jack, we assume that each variable has some inherent noise. And we can test two hypotheses. We can assume that the error in the first paradigm, the assumption in the first paradigm, why this is surprising and why people got excited, and you should too, I think, because up to this paper, the strong dogma in causal discovery was that for two variables, you cannot ever orient the edge. It's just proven. There is a proof of impossibility proof. It's impossible. Impossibility proofs have their own assumptions, change assumptions, and you can do it. The non-Gaussian noise condition allows you to say this. So imagine you run ICA, you have X and Y measurements, they are mixtures. And you run ICA and you establish those independent noise components. And here, well, I mean, they're the same. So in this graph, Y depend on epsilon X on the noise of X, because the noise flows into Y, the noise of X flows into Y. In this graph, noise of X, the independent component, does not depend on Y. It cannot. It only X can depend on noise of Y, but Y cannot depend on noise of X. There is no backflow. And if you have the dependence, then you can reject this hypothesis between Y mixture and epsilon component. So that's the principle. But then you can scale it up to multiple, like a complicated graph, causal graph, and simple and beautiful. But this is only intuition. Of course, they prove everything, and they have an efficient algorithm, and so on and so forth. But the next one is also surprising and interesting. Take the same example as before. Now, nonlinear additive noise. Well, in both cases, we had the additive noise. We had AX plus noise. Add a nonlinearity here. And in this model, surprisingly again, you can uniquely identify the graph. That was another surprise. And look at, I should kind of screen, don't look down, just look at this. This is our common Gaussian, that our common assumption. No matter how you slice it, it's still a Gaussian. That's why no matter how we look at it under which projection, it's still a Gaussian. So either it's conditional P of Y on X or conditional P of X on Y, nothing tells us the difference. But if we apply nonlinearity to the transform, then suddenly, depending on whether it's P of Y of X or P of X of Y, everything changes. So imagine what we assume is independence of noise, in a sense. If we have a relationship, a true relationship, and the noise on Y, imagine X causes Y. So then, no, Y causes X, I guess. The thing is, I'm trying to give you another intuition, but my interface froze. But the thing is that the variance at each point of X will be the same for Y. But if you flip it and look at the variance of X with respect to as a function of Y, you will see nonlinear interaction dependence that, oh, look, the variance changes as the, can you hear me, by the way? I've like everything froze from my point.
I can hear you.
Yeah, but that's my last slide. I can continue. Yeah, so that was surprising as well, that result. And we can talk about other stuff later. Yeah, okay, so that's all I wanted to say about this specific paper. It kind of super nicely summarizes everything in just one concise document and connects the dots. I really liked it, and if you kind of got intrigued about what I say, what I said in this, okay, now it works. I'm back, but my video is frozen still. I highly recommend reading that paper.
Do you think it's possible? So like instead of doing an experiment, can you just inject some nonlinear noise